going way over to the right, which is good. Okay. Yeah, so I would say suppose that this does converge. Okay. So by way of contradiction, suppose that n cubed over n squared plus 2n minus 7 does converge. Let's say it converges to x. So just put a number on it here. Let's just say that somehow that does converge to x. Okay. Right. So now what? That means that if it does converge to x, it means that given any epsilon greater than 0, I'll be able to find an n naught such that the absolute difference between these two things is less than epsilon. The trouble is that I don't know what x is, and the difference between these two things less than epsilon is going to look like a pretty messy expression. It's going to look like a pretty messy expression. So I'm going to suggest we do something a little different, which is we try to use the limit theorems. Okay, so I'm just going to respond to a quick text about something. So how could we use the limit theorems? Use the n squared? Yeah, that's exactly what I would do. So the point is that if we make another sequence, so also yn, so you said 1 over n squared, we know that 1 over n squared converges to 0, of course.
I'm sorry, I was like dividing by n squared, so you get rid of this n.
Oh, you just want to change, you don't want to make another sequence, you just want to change this. Okay, so I can rewrite this as n over 1 plus 2 over n minus 7 over n squared. Well, it doesn't really equal n, right? It doesn't, that's the thing, it doesn't quite equal n. But, so we're saying, suppose that does converge to x. Okay, so let me just write that down. N divided by 1 plus 2 over n plus, minus 7 over n squared. Let's suppose that converges to x. Okay. So, of course, 1 converges to 1, 2 over n converges to 0, and 7 over n squared converges to 0. So the denominator converges to 1. But we also know the numerator is not going to converge. So I can't use my limit theorems when I have one part that does converge and one part that doesn't. So I'm assuming that the whole fraction converges. Okay, but here's the thing. The denominator converges, and the whole fraction converges. That sounds like two things that do converge, right? So in other words, I could make another, so I could call this is xn, right? That sequence. I could make another sequence which would be yn, which is 1 plus 2 over n minus 7 over n squared, and I could say by the limit theorems, that converges to 1 plus 0 minus 0, which is 1. Right? I could do that. Agreed? Okay. So we could certainly do that. So y sub n converges to 1. So xn converges and yn converges. So what could we do? I could multiply them together, and the product would have to converge as well, right? So thus, xn yn would be, well, it would literally be equal to n, right? And that would converge by the limit theorems again. So I'm using the limit theorems a lot here. By the limit theorems, that would converge to x times 1, which is just x. But no, not 1 over y, just yn. So here's what you have up here. xn is n over yn. And I'm now going to multiply it by yn. Yeah. Exactly. That make sense? Okay, so if by way of contradiction, our sequence converges to x, then guess what, guys? N converges to x. Okay, however, that's going to be easy to disprove. Okay, it might even be one of your homework problems. I can't quite recall for the next assignment. So N converges to X. Let's just see if we can get a contradiction for that. I claim that's a contradiction. This means that for all epsilon, there exists an N naught such that yada, 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 yada. So let's pick an epsilon that's really small, or that's small enough. Let's try 1/2 again, maybe. Okay. I'm going to contradict this right now. It's so obvious it should not be true. But let's try to write it down. Okay, let epsilon be equal to 1/2. Then there exists an N naught in the natural numbers such that if N is greater than or equal to N naught, then the absolute value of N minus, so that basically these are the terms of the sequence, right? So N minus N naught, right? I'm sorry, N minus the limit. Sorry, the limit is X. N minus X is less than 1/2. Okay? I'm going to erase just a little bit here. We're trying to just get a contradiction out of that. So what do we have, guys? We have that, N naught minus X is less than 1/2, for example. We know that. But then every term after that is also less than 1/2 from X. So N naught plus 1 minus X is less than 1/2. Right? And if we want, we could put N naught plus 2 minus X, N naught plus 3 minus X, N naught plus 4 minus X. All of those terms are absolute value difference less than 1/2. So what we can do is we can add these together. We've seen this kind of trick before, right? Notice we can add them together, especially if we switch the sign on this first one maybe, right? So notice that the absolute value of X minus N naught is, let's do that one, plus the absolute value of N naught plus 1 minus X is less than 1/2 plus 1/2, which is 1. And now what I'm going to do is I'm going to make the left-hand side smaller by using the triangle inequality in reverse, right? So I'm going to basically make a single absolute value here that's going to now be less than 1. So what is that going to look like? Well, it's going to be X minus N naught plus N naught plus 1 minus X, right? So I'm putting these together and these together like that. And look what you proved. 1 is less than 1. Contradiction. Okay, so that might be one of your homework problems. I can't quite remember. But at any rate, if it is, here you go. Assume it converges to something. Assume that N converges. Pick an epsilon of 1/2. If you picked an epsilon that wasn't small enough, you can always, once you run through the proof, modify it. Just change it out for something smaller. But it turns out 1/2 is just small enough, right? And then all of these N values greater than or equal to N naught have this property. These are a bunch of integers, and we're trying to say that every integer is less than 1/2 of a unit away from X. Well, that just can't be true, because these integers are moving 1 unit at a time, bigger and bigger and bigger. You with me, Vivian?
Yeah.
Getting it? Okay. Is everybody with me? Yeah, Sal?
Quick question. So you already raised this part, but
Uh-oh.
when we got that N converges to X,
Yeah.
and we say that X of N or X subscript N, it was just because we divided by.
Yeah, this was equal to N over 1 plus 2 over N minus 7 over N squared.
So we just let the top be X of N?
This whole thing is X of N. This whole expression is X of N. What I did is I took that whole expression,
No, I see.
you got it?
Yeah.
And then I multiplied X of N by Y sub N,
Which was the denominator.
which was the denominator.
Right, okay, I see.
Right, and the denominator Yeah, the denominator definitely converges to 1, and this part definitely converges to x. So the product converges to x, which is what this says. And that's where you start to realize how the contradiction's coming. That's where the contradiction comes. Okay?
Okay, thank you.
Make some sense?
Yeah.
Okay. Let's try another example. Try one more example here. So let me do part B. So xn equals 2n minus 3 over 3n plus 5, all cubed, plus 1, all over 3 times 2n minus 3 over 3n plus 5 squared minus 2n minus 3 over 3n plus 5. And I need to, I think, move this camera back out a little bit. So I kind of zoomed it in. Okay, so there's part B that we're going to solve right now. Okay, so let's see. This is intentionally ugly looking. Okay. Any suggestions as to what you're going to do? Please don't tell me you want to use the epsilon definition. We'll be here all day. We don't want to do that. Okay, so anybody have any suggestion here? Substitute, what do you mean?
There's a lot of 2n minus 3 over 3n plus 5.
Mm-hmm.
Can we do the sum divided by, no, first part of the sum divided by everything in the bottom plus 1.
So like this one?
We
How about we just figure out what this converges to?
2/3 of everything.
Right, so just figure out what this converges to and then use the limit theorems to just plug it in. Actually, this is an easy problem. It just looks terrible. But if you use these limit theorems, it becomes one of our themes right now in these examples is the limit theorems really make life easy, right? So to prove what this converges to, what do you suggest I do? Divide through by n, right? So 2 minus 3 over n all over 3 plus 5 over n. And now you can say this converges to 2, so that converges to 2 minus 0 over 3 plus 0, which is 2/3. Okay? 2/3. Now, by the limit theorems, xn would converge as long as the denominator is not converging to 0. Let's see, this is going to be 3 times 2/3. Let's just check the denominator. 3 times 2/3 squared minus 2/3. That's not 0, is it? It's like 4/3 minus 2/3, which is 2/3. Okay, so we're safe on the bottom. We're using the product of sequences here. We're doing scalar multiple. We're doing subtraction. Remember, the limit theorems handle addition, subtraction, scalar multiplication, multiplication, and division. All of those, and that's all we're using right here. Okay? And then on top, we're going to have 2/3 cubed plus 1. Okay? So you just have to work that out. You just have to work that out. So it becomes very, very simple, and the answer is, at the end of the day, I'll let you check it, 35 over 18. 35 over 18. Okay, so that was not so bad. That one was not so bad. Okay, let's try one more of these, and then we'll move on to some different topics. Try one more that's maybe a little bit more interesting. Okay, part C, I wanted to, so this one converges, by the way. Should have said that. What a nightmare it would be to prove it from the definition. I don't know how we would do it. Put it on a computer, maybe it could figure it out. Okay, so here's another one. Let's let xn equal the nth root of 1/2. That's a little different. So we have, the terms are going to be you know, if I list the terms of the sequence, when n is 1, you just get 1/2. And then when n is 2, you get the square root of that. And then when n is 3, you're going to get 1 over the cubed root of 2, 1 over the 4th root of 2, 1 over the 5th root of 2, and so on and so forth like that. Right? So that's the way the terms look. And see, because we have roots here, we're not going to have any limit theorems this time. We can't really just, because the limit theorems are talking about addition, subtraction, multiplication, and division, and this is not any of those. Okay. So with this in mind, to think about this, do you think it converges?
The denominator gets smaller.
The denominator is getting smaller, so these terms are actually getting larger, aren't they? They're getting larger. So, but how much larger are they getting? Are they blowing up to infinity? Sorry, just a second, guys. My friend is trying to figure out whether we're getting picked or not. I'm just distracted by this thing. So I actually, so think about what you think this converges to, and then think about it. We're gonna prove it. I'll be right with you. I promise. I'm kind of stressed out here.
Then if you ever multiply a number of 57 times to get 2, it'll be pretty close to that.
Okay. All right, I got that sent now, so I'm good. I don't know whether we're getting it or not. My friend's going to find out. Okay, hopefully. Okay, so did you guys figure out what you think this converges to? To 1. Yeah, this is approaching 1, right? From below. So each of these roots of 2 is actually getting a little bit larger, but they never actually get above 1. But they approach 1 from above, and so as a fraction, these terms approach 1 from below. So the claim then, the claim is that this would converge to 1. Okay, does that make sense? So now we have to try to show it. Okay, so we don't have any limit theorems, so what else do we have? Anything?
Rewrite it.
Hmm? Rewrite it?
2 to the 1 over.
Okay, this is 2 to the negative 1 over n power. This is on the bottom fraction. Okay, we have that. I don't know if that really makes me feel any better. Just a different way of rewriting it. It's okay if you like it better that way. See, now that's getting into all this stuff that's like intuition, and we didn't talk about it in this class. And so I want to stick to the stuff You might have intuition about why this should work, but we need to make a rigorous argument here, right?
Which is the definition.
Pretty much. We're going to want to just use the epsilon definition. So let's let epsilon greater than 0 be given. Okay? And then we're going to do our usual scratch work backwards. I'm going to write down the scratch work first. And then go from there. So in the scratch work, let's see, how's this going to work? We're going to want to make the absolute value of 1 over the nth root of 2 minus 1. We want that to be less than epsilon, right? This is what we want. So we're working backwards for a second. Okay? So we can try and do a bunch of steps here to unwrap this thing backwards. We'd like to solve for n, really. That's what we want to do here. Solve this for n. So if I put negative epsilon less than 1 over the nth root of 2 minus 1 less than epsilon like that, then we can go at it from that point of view. So you always want to be comfortable. If you're trying to get rid of absolute value bars, this is the way to do it. Put the positive and negative epsilon in there. Okay. And we want to solve this for n. So what would you maybe suggest we do from here? Add 1 to both sides. To all sides, I should say. Add 1 to all sides. So 1 minus epsilon less than 1 over the nth root of 2 less than 1 plus epsilon. Okay, so it's going to look like that. Okay. I'm trying to solve this for n. Okay, take reciprocals of everything. Okay, so I could take the reciprocal of everything here. So if a is less than b is less than c, then 1 over a becomes greater than 1 over b becomes greater than 1 over c, right? So we'll just flip everything over. 1 over 1 minus epsilon greater than nth root of 2 greater than 1 over 1 plus epsilon. So that would be one way to try to work with it.
Log.
Pardon me?
The log.
Yeah, we're going to have to use the logarithms here. We're going to have to use the logarithm. This is really 2 to the, okay, now I maybe do like your idea. 2 to the 1 over n power. We take the log of everything, then what we'll get is the log of 1 over 1 minus epsilon greater than, now, so the log of this, I'm going to use my log properties. I can pull the exponent down in front, right? So 1 over n times the log of 2, and then greater than the log of 1 over 1 plus epsilon. It would look like that. Make sense? Now what? Take reciprocals again?
Divide the log probably first.
Say again?
It's probably better to divide the log first.
Okay, we can divide by the log. Which log do you want to divide by?
Log 2.
Log of 2. Okay, so let's divide through by the log of 2 everywhere. 1 over n, the log of 1 over 1 plus epsilon over the log of 2. So this is a little messy, but it's working. Okay, I think my camera needs to be turned though at this point. Just sort of show what's going on over there. Okay, we're just doing a bunch of steps to try to solve for n here. It's a little bit hard to read that, isn't it? So essentially I have a chain of 3 inequalities. Log of 1 over 1 minus epsilon over log of 2 is greater than 1 over n is greater than log of 1 over 1 plus epsilon over log of 2. So now what? Flip it again. Okay, flip it back over again. So now we have a log of 2 on top, log of 1 over 1 minus epsilon on the bottom, less than n, less than log of 2 over the log of 1 over 1 plus epsilon. Okay, so we end up with something that looks like that. Okay. Does that make sense?
Right.
Anything close to what I got? Yeah, I think that's good.
You could do some sort of, like a ceiling function.
Yeah, so basically, you want to work with this one, right? N has to be at least something. I'm not so worried about this side. So really, I want to choose my N naught. I'm just going to say choose N naught in the natural numbers with N naught bigger than log of 2 over log of 1 over 1 minus epsilon. I'm just gonna do that.
You'd have to make the argument that like epsilon is small, but then you don't want
Yeah, there's a problem if epsilon is equal to 1, for example. You can assume that epsilon is less than 1, though. And that's because all of these terms are, if we're claiming that the limit is 1, and if I choose an epsilon that is that wide or wider, every single term of this whole sequence will be inside of that neighborhood. So if epsilon is big, then we've got no problems. So it's really, you could actually almost do it in 2 cases. If epsilon is at least a half, then all terms are inside, that interval, basically. Can I step outside for just a quick second? I'll be right back.